Okay, so hello and welcome to a new series of discussion. So this discussion will be on convection heat transfer and that is very interesting. Okay, so we will try to learn from very basics. Okay, so at first I will introduce you with some new style of writing equations. Okay, so that is called the index notation. Okay, and also uh, some formal name is given to that is Einstein indices. Okay, so what do we mean by that? So first of all, let me tell you that if you study tensor algebra or tensor calculus, then you are bound to study these index notations. Okay, and tensors are useful when we deal with some continuums like fluids or solids. Okay, so if we are dealing with any continuum, to deal with that continuum, to deal with the dynamics or kinematics or anything, this tensor calculus or tensor algebra is very useful. Okay, so let us see that how we can apply this index notation and tensor algebra or tensor calculus in our convection study. Okay, so we'll start by something which is denoted by index notation representation. Okay, index notation representation. Okay, so not only in heat transfer, okay, in in fluid mechanics also, or even in maybe thermodynamics, in some cases of thermodynamics, this index notation can be useful. So first of all, what is the objective? The objective will be clear uh, immediately after I introduce this thing. Okay, so first of all, how can we write a vector? Okay, so if A is a vector, let us say that A is a vector, capital A. Sorry. Okay, so let me erase this. Okay, so if capital A is a vector, okay, so in 3D, okay, so it is in 3D. So that directly means that A has three components. A has three components, right? So if I draw the coordinate system, okay, like this, and if I name it like so, this will be my I cap. Okay, this will be my, let us say, j cap, and I'm not satisfied with the coordinate axis, so I'll create my own k cap, right? Okay, so this is essentially the x axis, this is y, and this is z, right? So A has three components written by ax along x-axis, ay along y-axis, az along z-axis, right? And I can write these things, okay, in another format. In what format? Let us see that if I write this x-axis as x1 and y-axis as x2 and z-axis as x3, okay, then the same components I can write as, okay, maybe a1, a2 and a3. Okay, so I can write this a vector as a1 I cap, okay, plus a2 j cap plus a3 k cap. Okay, okay, So now this vector can be represented as AI. Okay, what do you mean by AI? So this can be represented as AI, and this I can take values 1 comma 2 comma 3, right? So what do you mean by this AI? So now A is a vector, so this is a vector. Okay, okay, so this is a vector, and essentially we can write it as, okay, so A equal to AI EI. Now what is this? This looks confusing, right? But it is not, it's very useful and easy. So this is the essence. Now this is a vector, and this AI is nothing but a component. Okay, the so this is the ith component. So more specifically, this is the ith component. Okay, and what do you mean by this? So EI is the unit vector in ith direction, in ith direction. Okay, in ith direction. So how can we write A? That is, if ei cap is the vector in ith direction, then formally in the full form A is equal to A1 E1 cap plus A2 E2 cap plus A3 E3 cap. So this E1, E2 and E3 are essentially I cap, J cap, K cap, right? We are writing this for the sake of writing it in indices notation, more specifically to simplify it. Okay, so now uh, but the thing is that instead of writing this, we write A as, okay, A is equivalent to AI. Okay, A is equivalent to AI. So whenever we are writing AI, or maybe AJ, or maybe AK, or maybe BM, or maybe BN, so this, all these things, this I, this J, this K, this M, this N, these are called free indices. Okay, so these are called free indices. And why do we call these free indices? Okay, because these indices are free. These indices are free to take any value out of what? Not any value, 1 2 3. So any free indices can take only 3 values. Okay, so free indices means, and other thing is that there is a rule for a free indices. Okay, so now as I have introduced the thing free indices or a free index, what do you mean by a free index? So uh, I am just taking this off. So this will be our first point. Okay, so this is the first point. The second point is, uh, in any term, in any term, uh, there will be there will be okay, uh, only one unique free indices, free index. So what do we mean by this? This means that we can write AI. Okay, so in a white background, I don't think this is a correct ink. So if this is AI, then I is a free index. Okay, let us write. So then this is a free index. But if I write AII, then this I or this I, both of them, okay, not free index. And what are they called? I will talk about later. Okay, but if I write Aij, again both I and j are unique, they are not repeating. Okay, so both of them are free indices, right? I hope up till this it is clear. And if I write ijk, then again all the three are, okay, all the three are free indices. So now if I write I, j, again maybe j, again k, okay, or maybe what makes more sense. So if I write an equation, okay, so ai, so if I write an equation, maybe, okay, ai plus b, let us say ij, okay, ij cj, okay, equal to 0 maybe, okay. So then uh, this has one free index, okay, index, and this is a whole term. So I have used this word term, and term means if I write x square plus 3xy plus 4 e to the power z, then all of these are terms. That is, each entities or each numbers or each parameters are multiplied or divided with each other. Okay, so all these are terms. So this is a term and this is a term, right? So in this term, this j, so j is not a free index, right? But this I is a free index. Okay, nice. I hope up till this it is clear. If not, let me know in the comment section. I will try to elaborate it more in the next video. And now I am proceeding. So the main thing is that free index cannot repeat. Okay, then it will not be a free index. So uh, this thing is equivalently saying, so let me use another color, that is okay, free index cannot repeat, cannot repeat in a term. So don't have this this confusion that if I have here ai, then I cannot have a bi. So I can have ai plus bi. So this is one term and this is other term. So both terms I can have, okay, and in each of the terms I have the free index I. But I cannot have ai into bi, and I am saying that I is a free index. I cannot say that. Okay, so in this expression both ai and bi are separate terms and they are having the free index I. And in this expression this is a single term having something that is not a free index, and what is that, that I will tell. Okay, okay, so now let us come to the concept of the repeated index. Okay, the repeated index. Okay, so I was uttering that this is not a free index, and I will tell that what is that, like this expression. Okay, so let me now take the same expression as this, that is ai plus bij cj, okay, equal to 0. So I have told that in this term I have one free index, right? And in this term also I have one free index. Then this j is occurring twice or more than once, okay, more than one it is occurring, so this j is called a repeated index. So essentially a repeated index will repeat will be repeated will be repeated more than once in a single term, right? Okay, so if this is the uh, rule of the repeated index, then we have to know that what is the application of this repeated index and what this index mean. Okay, this means, okay, so let us say that I am writing a dot b. How can I write this? A1 b1, right, A2 b2, and A3 b3. So by this time I think you are clear that what we mean by a1, a2, and a3, and b1, b2, b3. So these are the components of the vectors a and b along the x, y, and z directions, right? So I can write this as, okay, ai bi. Okay, so ai bi means, and okay, so we are familiar with this notation, right? ai bi. So now we are clear that this thing means this total thing, right? This total thing. Okay. So according to Einstein indices notation, this thing we will write as AIBI. So whenever we see any repeated index, then that means that we are applying the summation over that index. Okay, we are applying the summation over that index. So this is the significance of the repeated index. So if k is a repeated index in a term, then then uh, we will sum that term for k equals to 1 to k equals to 3. Okay, because any index cannot take values above 3. Okay, so in this expression, now again I am writing the same expression, ai plus bi plus, okay, bij cj. Okay, so this is ai, this is a vector, and this is essentially means, so I can take any value, right? So that is the significance of a free index. So this essentially means bi1 c1 plus bi2 c2 plus bi3 c3, that is and that is essentially bij cj, j is from 1 to 3, right? So that is the summation is applied over the index j. So this is the significance of the repeated index. So I hope this is clear. And one more thing I would like to emphasize on, that is this repeated index will be repeated more than once, that is it can be repeated thrice or four times or five times, anything. Okay, so like for an example, if I write b I j k, okay, c j, um maybe dk, okay, so that is mean, so that will mean that this is a double summation, this is a double summation, okay. So the number of the repeated index, the number of the separate repeated index will denote the number of separate summations, okay. Another thing that it is also very obvious that whenever I am applying this repeated index, then this is equivalent to, this is equivalent to akbk or ajbj, okay, because essentially all this boils down to the summation over I or over k or over j. So it doesn't matter that if you write I, k or j or any other alphabet to indicate the repeated index, right? Okay, so now let us uh, do one more thing, that is uh, tensor, okay. So we have something called scalar, right? So scalar means only magnitude, we have only magnitude, right? Have only magnitude. And then we have something called vector. So vector will be specified by magnitude plus direction, right? Okay, so then we have tensor, okay. So tensor will have magnitude obviously, okay, plus maybe direction 1 plus direction 2, okay, direction 2, okay. So we can say that the scalar is having magnitude plus no direction information, okay, or magnitude plus zero information, okay, or I'm just writing this because this will help, magnitude plus no direction or no information, okay. And vector has magnitude plus direction, um, plus no direction, so it has only one direction, okay, or no information. And this direction, so the either direction or information, I will use these words interchangeably, okay. And tensor is having magnitude as well as direction 1 or information 1 plus either direction 2 or information 2 it is having, okay. So I can say that, or I can represent it, I can represent it by scalar by a zeroth order tensor, okay. I can represent this vector as a first order tensor, okay, first order tensor. And I can I can represent this tensor as a second order tensor. So tensor is more generic form, and we can have also third order, okay, and we can have also fourth order tensor, okay. So now let us continue from this terminologies. So a zeroth order tensor will have how many free indices? This is the first question. So I will free indices. So number of, right, number of free index or free indices, right? Okay, so a zeroth order tensor will have no free indices. Okay, a zeroth order tensor will have no free indices because now free index means another information, right? The moment I say that I have AI, then I can have A1, A2 or A3, and those three will be the components of a vector or a first order tensor A. Okay, so and the moment I am saying that I am adding some Aij, that means I can take value from 1 to 3, and for each value of ij can take value from 1 to 3. So Aij will have 9 components, right? 9 components. So Aij will have 9 components, right? So the number of components is increased if I increase a free index. So a free index is denoting an extra information or an extra direction. Okay, and if I say Aijk, then it will have how many? 3 into 3 into 3, that is 27 components. So an nth order tensor, nth order tensor will have 81 components, right? Nth order tensor will have 81 components. Okay, so a zeroth order tensor or a scalar will have 0 free indices. A first order tensor or a vector will have 1 free index. A second order tensor will have 2 free indices. A third order tensor will have 3 free indices. A fourth order tensor will have a 4 free indices, and so on. Okay, so this is essentially a scalar. So this is a scalar. Okay, this is a vector, this is a second order tensor, no special name, second order tensor, third order tensor, and a fourth order tensor. Okay, so we know that what is a scalar, what is a vector, and what is okay. Now second order tensor, we can give example of stress. Okay, so in fluid mechanics, I hope that if you have gone through the derivation of the Navier-Stokes equation, then in most of the books, if you go by the most general way, then you have to deal with this term sigma ij. Okay, and because this is the stress, right? And if I have spoken about this, then I must say that is a vector called traction vector. Okay, so this is a vector actually. This eta uh, is not correlated with the components of this ti. Okay, so this I here is the free index, and a third order tensor is epsilon ijk. Okay, this has a separate value. Okay, so this is represented, uh, I mean the application of this epsilon tensor is uh, when you use the curl, okay, or a cross b. Okay, um, so you can look for this, sorry. Okay, so you can look for these tensors in your in any of the books or in any internet, in internet. So I will talk about each of these tensor whenever required. So because this class or this discussion is not dedicated to tensors, that is why I will not dive down deep on the topic of this epsilon tensor or any other thing, because we have a fourth order tensor also, that is the modulus tensor. Okay, CIJKL. So I'm sure that uh, if you have, as I have said earlier, that if you have gone through the derivation of the Navier-Stokes equation in the most general way or in the most general path, then you must have uh, you uh, you must have been acquainted with these three terms, that is this and this. Okay, and so now let us proceed. Okay, so another thing, that is a term means if I am saying that del xi, del maybe del yi, then also this is a term, because essentially, I mean, this is analogous to a division. Okay, so this will mean this del xi, del yi, I runs from 1 to 3. Okay. Okay, so now let me tell you about a very important theorem which converts the Lagrangian point of view to the Eulerian point of view. Okay, so if you have studied fluid mechanics, then then surely you have studied about this. Okay, so this is nothing but the celebrated Reynolds Transport Theorem. Okay, so sorry, Reynolds Transport Theorem. So essentially this theorem converts the Lagrangian point of view to the Eulerian point of view. Okay, and so in energy equation we can derive the energy equation with or without the Reynolds transport theorem. So I will explain you both of the topics, both of the ways. Okay, but as I will also use the RTT, and that is why I will describe you about the RTT, how and from where it comes. So let us have a system, okay, like this, an arbitrary system. Okay, so this is the system at time t. Okay, now the system from time t, it goes to time t plus delta t. So maybe this is the system at time t plus delta t. Okay, so and we will denote our control volume as this. Okay, so the choice of the control volume is in our choice. So this is our CV. Okay, so the system goes from time t to time t plus delta t, right? Now let us uh, divide this three segments and we name it as, so this is the segment 1, and this is segment 2, and this is segment 3. Okay, so segment 1 and 2 togetherly they denote the system at time t, and the segments 2 and 3 they denote the system at time t plus delta t, right? Now if I have to define any property in the system and the change in the property actually, okay, so rate of change of a property n, and a very important point is this n must be conserved. Okay, so this n can be a vector, can be a scalar, but it should be conserved. So This we will denote by, okay, del n by del t of the system, and we will apply the limit del t tends to 0. Okay, so this is nothing but dn dt of system, right? Now what will be this? From the basic calculus, this will be uh, n of the system at t plus delta t minus n at t by del t. Okay, and now we know that n at 3 plus n at 2, that will denote n at t plus delta t, and n at 1 plus n at 2, that will denote nt. So application of these two relation, we will apply this in this line. Okay, so we will get n3 plus n2 minus n2 plus n1, right? So this is at time t, this is at time t plus delta t, right? Okay, so by delta t, and so I have make a small silly mistake, that is this will be limit delta t tends to 0, and here also limit delta t tends to 0. So again, limit delta t tends to 0. Okay, so what is remaining? Now we are having again another mistake. Sorry, I apologize for this mistakes. T plus delta t. Okay, so this is the t plus delta t part, that is this, and this is the t part, right? So that will be n of 3, right? And okay, so plus n of 3 at t plus delta t, right? And n of minus n of 1, right? Minus n of 1 at t, right? This by delta t. Okay, and plus again limit del t tends to 0. Okay, del t tends to 0, and this is n of 2 at t plus delta t minus n of 1 at t, sorry, n of 2 at t. So just check if the algebra is correct or not. Okay, so now what is this part? From the basic definition of calculus, what is this part? So this part is nothing but, so n of 2 is this, so this 2, sorry, this 2 is denoting the what, CV, right? So this part is del n del t of 2, right? So I'm writing here 2, and if I remove the 2 or if I don't, this is the CV, right? This is in the CV in the control volume. Okay, now the thing is, I have segmented this system in 3 parts according to the time flow. The time is flowing from t to delta t to t plus delta t. Now if the delta t tends to 0, okay, then this system shown by the green boundary, that is system at t, and the system shown by the blue boundary, that is the system at t plus delta t, these two will merge at the limit del t tends to 0, and this is the pivotal concept here. Okay, So the same concept is applied whenever we are um, merging the concept of the Lagrangian or Eulerian, okay, point of view. The derivation of the acceleration of a fluid in terms of the Eulerian variables also take advantage of this concept. Okay, so now in the limit, so just remember this. So note, okay, so note is in the limit delta t tends to 0, okay, the systems at t and t plus delta t coincides, systems will coincide with the CV, okay. So all this n3 n1, this will be with respect to the CVs, okay. And I mean whenever we are applying this delta t net tends to 0, so from this line I can directly write, that is equal to, now this n3 at t plus delta t, okay, that is this part, right, that is this part, right. So this is like the rate of change of n at the segment 3, right. And if you see that at the limit delta t tends to 0, this blue boundary is coinciding with this green one, right. So essentially this means that this segment 3 means that some part of n is going out from this green boundary, okay, some part of n is going out from this green boundary. So this is the outflux, from the control volume, because this green boundary is the control volume, okay. uh, and this green boundary is the boundary of the control volume chosen, and according to the similar concept, this part will be the influx with respect to the control volume, okay, such as uh, the flux of the property n is going inside the control volume, okay. So this part I've spoken about this part, that is this is flux going out from CV, right, and this part is flux going in to CV, okay. Okay, so okay, so now directly I can write this as, okay, the flux going out, uh, so this is n dot, okay, n dot out, flux going out, minus n dot in, okay, plus del n del t CV, okay. So this fluxes can be written as, now how can we write this, now consider this as your system, or this as your CV, okay. So this is your CV, consider a small elemental surface, so this is your dA, okay. So if the relative velocity, the mind the term, the relative velocity is in this direction, okay. the relative velocity of the substance. Okay, v relative. So this is the relative velocity of the substance. Okay, and maybe this is the area. This is the area normal. So the area normal I should denote by this color. So maybe this is the area normal. So I think I should switch the area normal because this is more likely to be the area normal. So this is n cap. So this is the area normal and this is the velocity relative to the control volume. So this is velocity of the generally the fluid. Okay, but it is true for a solid also, but generally the the fluid will flow only. So the velocity of the fluid with respect to the control surface. So this is the control surface and this is the control volume. Okay, now if we know this, so then what will be the mass flow rate? Okay, so dm dot, so that will be rho, that is the density of the fluid, and v relative, right, dot dA vector, and area vector is given by its magnitude dA and n cap, that is area normal. So v dot n into dA, right. Now you don't have to uh, take any tension about whether the flux is going in or out, because you have to put a minus or plus sign, right. But here if the v and n are in the same direction, okay, that is if the angle between them, this angle, so if theta is less than 90 degree, then this dm dot will be positive, right, dm dot is positive. And if theta is greater than 90 degree, that is the velocity and the area normal are in opposite direction, so then the flux should be inward, that is negative sign. So this v dot n thing, this thing will take care of the sign. Okay, so this thing is taking care of the sign, correct. Okay, so if this is clear, then the flux, okay, incoming, so the flux of the property n through dA, this is the elemental surface element. So this will be, so now let us define n by m equals to small n. Okay, so small n is nothing but mass per n per unit mass. Okay, specific n. So this is the, so if n is the extensive property, then n is the intensive property. Okay, so this will be what, rho v relative dot n cap into dA. So this is the mass flow rate. So mass flow rate into small n, that is so this is the mass per unit time second, and this is n per unit mass. So all total is n per unit second. So that is the flux. So this is the flux, and there can be many other fluxes, like we can choose a dA here also, and maybe something is going in, maybe from this dA something is going out. So to take care of all these fluxes, we have to put a, so the total flux, right, the total flux through the control surface. Okay, total flux through the control surface. So this will be integral of rho n v relative dot n cap dA, and this integral will be over the control surface. Okay, so this is the term. Okay, I mean what I have derived is expression for this. So expression for this is rho n, okay, v relative dot. Okay, so I am not writing n cap anymore to avoid the confusion. Okay, and dA. So this is the control surface, and this n we can again write as rho small n dv, right, over the control volume. I think this conversion, I mean, I think this conversion is pretty obvious. So all over the equation becomes, all over the equation becomes dn dt of the system is equal to what? ddt of rho n dv cv plus rho n v relative eta cap dot dA cs. Okay, so this is the Reynolds Transport Theorem, and this is very important. Okay, so this is the Reynolds Transport Theorem. Okay, um, so now let us move to the convection, that is the energy equation derivation. So let's now proceed. Okay, so energy equation. Okay, and this is nothing but the first law of thermodynamics. Okay, so this is nothing but the first law of thermodynamics, because energy equation means energy balance equation, and nothing more than that. Okay, so the first question should be that if this is energy equation and if this is equivalent to the first law of thermodynamics, then we all know the first law of thermodynamics, right? But uh, what we have studied as the first law of thermodynamics, the application of that law or the application of that equation is very limited to some closed systems. Okay, to some closed systems. Not only the closed systems, we can apply the same law for the open systems also, but some variations are needed. Okay, and here we will apply the law uh, to get some equation that will be governing the temperature of a flowing system. That will be our main objective. Okay, so essentially it will govern the enthalpy, and it will govern the uh, temperature for a special type of substances, and not the special type of substances, because these are the substance uh, which are mainly used for engineering purpose. Okay, so now let us proceed. So what do we mean by energy equation? So energy is something that can be conserved, right? Energy can be conserved, right? And if anything can be conserved, okay, so the main the main problem is, maybe we are defining a domain. Okay, we are defining a domain, and in this domain we have to derive some governing equation that is valid at each and every point of this domain. Okay, so I can do something, that is I can take an infinitesimal volume. So this is an infinitesimal volume dv. Okay, and I can apply the energy equation or the basic energy balance, right? I can apply the basic energy balance. So if I apply the basic energy balance, then I can also do that. Okay, so I will go by two approaches. The basic approach is the not sorry the first approach is by Reynolds Transport Theorem, RTT. Okay, I will start by RTT. So I can apply RTT on any quantity that is conserved, be it a scalar, be it a vector. In fluid mechanics, we have applied it on a mass which is a scalar, and also we have applied it on vectors like momentum or angular momentum, right? So now let us apply RTT. Okay, so let us apply RTT on n equal to E. So what is E? E is total energy. So this total energy means, this is very important, kinetic energy and internal energy. Okay, so potential energy will be potential energy for the molecules, okay, will be under the internal energy thing, okay. Or more specifically, kinetic energy, if we say that, uh, we should write this as mechanical energy, okay. So mechanical energy and internal energy, okay. So now, I have told that the potential energy will be categorized under the internal energy, okay. And this mechanical energy is essentially the kinetic energy, okay. So if I apply RTT on E, then I will get what? Del E, okay, del T system, right, equal to del T of rho E dV over the control volume plus CS, that is control surface, over the integral rho E, okay. So V relative dot N dA, right? So I can write this. This is the basic RTT, the Reynolds Transport Theorem, okay. So this term basically is the reason because of which the change in energy in any control volume or in any control system, because in this term I have system, so this term depicts the reasons for the change in energy in any system, okay. So now what can be the reasons? The first is, okay, the first is heat heat transfer, okay, heat transfer. The second is there can be heat generation, right, heat generation. The third is work transfer, right. I don't think that there are any other methods, okay. So now this work transfer can be shaft work, okay, shaft work or external work, okay, not external work. So this can be a shaft work or it can be a boundary work, right. So shaft work is not there and boundary work is there, right. And we will see that what do we mean by boundary work. I mean boundary work is the same. Okay, I mean boundary work means essentially analogous to some pdv. Okay, so here it is not a shaft work at least, and it is not exactly right or correct to term it as a boundary work, but still it is not a shaft work, that is we are rotating some shaft, so that is another issue that can also be incorporated here. Okay, but but the energy equation is not considering that. Okay, okay, so sorry. Now this heat transfer, how can we denote it mathematically? So let us concentrate on this heat transfer. So if I have this surface, or maybe this is a volume V body, and I have an infinitesimal surface. Okay, so this is dA, right? So this is dA. So heat transfer can be by some heat flux. So this dA is having some unit normal n cap. Okay, so this is the unit normal of dA, right? So and maybe some heat flux is going in this direction. So you should know that heat flux is a vector. We don't give an arrow over it, but it is a vector. Okay, so then the heat that is going out from the surface or that is going in, that will be so heat passing through the surface, passing through dA is q dot n. Okay, so this is q dot n in dA, sorry, q dot n dA, right? Okay, now if heat is coming in, then so by convention, okay, this is important. By convention, okay, heat coming in is positive and heat going out is negative, right? Okay, so if heat is coming in, now this case that I have drawn, for this case, so heat is going out, heat out, right? So heat out, um, it is if I follow this notation, then the direction of q and n here is positive. Okay, but this heat out should be negative, then I have to apply some extra minus here. Okay, so to obey this notation, I will say that heat passing through dA is what? Minus q dot n dA. I hope this is clear. Okay, because q and n, if it is in the same direction, then it will give plus, and n will be positive only when you are denoting it, it is denoting it as an outward normal, but outward heat is negative, so the whole q dot n should be negative. Okay, and that is why we are putting a minus. So this is the heat passing, okay, or heat transfer effect. I am removing this part. Okay, now this heat generation is pretty simple. If q if q triple dot is the heat generation rate per unit volume, then this is this. Okay, so just for the sake of completeness I will write it that this is the heat generation, okay, per unit volume, right? Okay, now this is very important. So in any system, in a in an infinitesimal control volume, okay, we are not supplying any shaft work out of, I mean, uh, from an external means, by an external means, okay. So then how we can um, express the work transfer? So in any continuum the work transfer can be by forces, right? The work transfers can be by forces. So in pdv there is a force uh, that is called a pressure force, okay. So and what type of forces do we have in case of fluids, okay, or maybe in case of solids? So generally in case of continuum, so this work transfer will be because of by by surface forces, by body forces, right? Okay, so now the surface forces, so surface force is denoted by something called a traction vector. So traction vector means what? Again, if I denote that this is a body, okay, and so this is again dA, okay, having an unit normal in this direction, okay. But the force on this dA, this infinitesimal surface, can act through any direction, right? So maybe this is the direction of the force, this is the direction of the force, okay. So this is the force denoted by Tn, okay, I cap, Tni, okay. So this notation I have introduced you earlier. So this n is the unit normal of dA. So this n is saying that this Ti is on dA, right? So just take your attention on these words, that this n is saying that this Ti on is applicable on dA, and nothing more than that, okay. So this n will not be added in the information for the components of Ti, okay, because whenever we are saying traction vector, then that means the surface is fixed, thus the surface cannot vary. For a tensor, this I, j, k is something that can vary, but for a particular traction vector, thus the surface is fixed, okay. So okay, and this I is the direction of direction of application of force, okay. So this is the traction vector Tni, and if you write it as Ti, then it is also okay, okay, because n does not have any other significance, okay, in terms of the mathematical manipulation. It is just a symbol for the sake of our understanding. If you are comfortable with Ti, then also it is okay. Now there is something called Cauchy's theorem, okay. So before Cauchy's theorem, I have to familiarize you with something called stress tensor. Okay, so stress tensor, so let me draw an axis here. Okay, so this is x, this is y, this is z. Okay, so if I draw an infinitesimal cube here, okay, just give me some time. You can skip this part of the video, or you can fast forward it. Okay, sorry. Okay, so this part you can consider. Apologies for this part. Okay, so now, so on this surface, so let me name it A, B, C, D, E, F, G, H. So in the surface, BFGC. So in this surface, okay, I can have a force in this direction, right? In, let me give any other color. So maybe this one. Okay, so I can have a force in this direction. Okay, so this force is in, so in terms of traction vector, so this will be, so this x I can write as x1, y I can write as y, sorry, y I can write as x2, and z I can write as x3. So this will be t1. Okay, because the unit normal of the surface BFGC is along 1, x1, and the direction of the force is also 1. So whenever the control volume is having the normals along the along the directions of the coordinate axis, then the traction vectors, or then the force per unit areas can be denoted by this notation, sigma 1 1. Okay, or effectively this is sigma ij. Okay, so this is applicable only when the surfaces along which the forces, the surfaces on which the forces are acting, okay, are having their unit normals along the coordinate axis. I again repeat this, that the sigma ij notation is only valid for the, if the forces are acting on the surfaces which are having their unit normals uh, along the coordinate axis, right? So essentially this I is, okay, direction of unit normal, unit normal, and this j is what, direction of application of force. Okay, so if I consider a force on BFGC in this direction, okay, then it will be what, it will be sigma, so acting on a surface that is having the unit normal in the direction of x1, so this is 1, okay, but it is having the force towards this x3 direction. Okay, the sense is different, but the direction is this x13. Okay, okay. Similarly, if I am having something on, maybe on another surface, so maybe I'm having some force on CGHD in this direction. So the surface is having its unit normal towards x2 direction, so it will be 2, and the force is along 3 direction. Okay, okay, then to specify all the surface forces on this unit volume, I have a matrix of sigma. Okay, and the terms of the matrices are what? Sigma 1 1, sigma 2 2, sigma 1 3, sigma 2 1, sigma 2 2, sigma 2 3, sigma 3 1, sigma 3 2, sigma 3 3. Okay, okay, so this is a second order tensor. Okay, so this is equivalent to sigma ij having two free indices I and j. This is also called as Cauchy stress. Okay, now our objective is to relate the sigma ij with, so sigma ij with n cap, where this n cap is not along either of x1 x2 x3. Okay, so n1 is not along either x1 x2 x3, because sigma ij is only valid for x1, I mean only valid for the surfaces having the unit normal along x1 x2 x3. But this, if this n is not along those, then what we will do, right? So we have to derive something, or more specifically, uh, I have this I mean, we will say that I have this thing, right? But the problem is that in any body there can be, I mean, countably infinite number of ends. Okay, if this is a body, so so this part is having unit normal along this part is having unit normal along this part is having unit normal along this part is having this, so there are various unit normals. So then we are having infinite directions, and along with that we are having infinite traction vectors, so our number of unknowns are increasing, right? But if I can correlate this tin with sigma ij, okay, tin with sigma ij, then I have only 9 unknowns, because sigma ij at max can have 9 unknowns. So I have to somehow correlate this tin with sigma ij, okay, to reduce the number of unknowns. So how can we do that, right? So all these things are actually taught during the derivations of Navier-Stokes equation, or in any other solid mechanics courses also, because these things are not bounded in the domain of fluid mechanics or solid mechanics. So these things are valid for uh, any continuum. Okay, so now let me draw again the coordinate axis to sorry, I'm extremely sorry. So let me draw the coordinate axis to establish the relation between the traction vector and the sigma ij, the stress tensor. Okay, so this time I will take a tetrahedron instead of a cube as my infinitesimal volume. Okay, and the tetrahedron will be having its three of its faces oriented along the direction of the coordinate axis. So this is our tetrahedron. So this is O A B C. So I am drawing now the forces. Okay, so you can see that the faces OBC, OAB and OCA are having their unit normals along x1, x2 and x3, that is the along the coordinate axis. So the forces on those surfaces can be represented in terms of the stress tensor. But for the surface ABC having the normal along any arbitrary direction, that is not in the directions of the coordinate axis, so for that we cannot write it as the sigma or the stress tensor. We have to write in terms of the traction vector, and thusly by applying a force balance we can establish a relationship between the traction vector and the uh, stress tensor. So that is the philosophy here. Now before doing that I would like to tell you something. So if I consider the forces on AEDH, that is on this surface, okay, on this surface, then what I can do? So uh, the convention is we will consider the force to be positive in the outward direction. Okay, so ideally the direction normal of this surface, that is AEDH, I will draw it by the green color. So this will be the direction normal n of AEHD, right? So this is opposite to the positive x1 direction. Okay, so according to the convention the positive force will be, okay, in this direction only. So this will be also the sigma 1 1. Okay, now you can argue with me that the force can act in this direction. Okay, so that will be denoted as minus sigma 1 1. Okay, so if you consider this sigma 1 1 as positive, then you will get your answer as something minus sigma 1 1. Okay, and that will denote that the force will act in this direction, right? But always the 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 direction of surface normal, okay, that will also dictate the positive direction of the force per unit area. Okay, now similarly if I am having, okay, the force may be in this direction, that is, okay, so the surface normal is in this direction, okay, that is opposite to the positive x1. Okay, so if I am having a force that is parallel to x3, then the positive force must be opposite to the actual positive x3. So this will be my sigma 1 3. Okay, sigma 1 3. And according to that rule, okay, so on this surface my positive sigma 1 3 will not be in that direction, it will be in this direction. Sorry, yeah, it will be in this direction, right? So the rule is, if the surface normal is towards positive xi, positive xi, then so I can take 1 2 3, then the forces will also be in the positive xj direction. And so actually I can take a bracket here, so positive xi or negative xi. Okay, and then according to that it will be positive xj or negative xj. So for an example, if my surface normal is in the direction minus x2, then the forces will be, then the positive forces will be either in minus x1, either in minus x2, or in minus x3, right? Like uh, in this cube, which surface is having its normal towards minus x2? Okay, that is AE, AB, FE, right? His surface. So if it is having its its normal towards minus x2, so I have to represent the force that is acting parallel to the x1 axis. Okay, so normal is in the minus x2, so the positive force will be in the direction of minus x1, that is in this direction, right? That is in this direction. So this will be the uh, positive sigma 2 1. Okay, right? So maintaining this convention, okay, now let me draw only the forces on each surface in x direction, or which are parallel to the x1 axis. So let me see that the force on OAC. So the OAC, okay, so let me draw a table here, OAC. Okay, so the table will contain the, okay, surfaces, then direction normal, right? Then direction of force, right? So surface OAC. So the direction normal is along minus x1, and the direction of force, we know that it is essentially we are considering parallel to x1 axis. Okay, so parallel to x1 axis, right? So it has to be in x1, so this will be sigma 1 1. Okay, but the direction will not be along positive x1, it will be along negative x1. And the reason, I think it should be clear by now, because it is having minus x1, the positive force should be in this direction. Now the surface OBC, the direction normal is towards minus x3, so sigma 3 1. Now sigma 3 1, okay, so similarly all these forces will having direction towards minus x1, so this will be sigma 3 1 acting on OBC. Similarly it will be OAB. Okay, now it will be x2 sigma 2 1, so OAB also will have this thing in this direction. Okay, so say, okay, 2 1. Now a, actually this ABC will have a general traction force. Okay, so a traction vector may be directed towards this direction. So this is this in ABC. Okay, any direction I cap or j cap, we don't know that, but we have to I am writing only the forces or the components of forces along the x1 sense, or the parallel to the x1 axis, right? So I will draw a force that is parallel to x1 axis. Okay, so we can see that the, if we project the area ABC, okay, in the x1 direction, then the outward normal will be in the positive x1 direction, right? So that is the actual outward normal is something in this direction. maybe. So this is maybe the outward normal. So if I project this outward normal like this, okay, so this is in the positive x1 direction. So the surface force that will also be in the uh, I mean the surface force, to consider it positive, we have to show it in the positive x1 direction. Okay, so then maybe this is, so this will be t n and 1. Okay, and these are the forces. So actually this will be into area of ABC, this will be into area of what, OAB, this will be into area of what, this is sigma 1 also OAC, this will be into area of OBC, right? So these are the forces. And another force, that is the body force. Okay, so body force in x direction, so we don't know that will be in the in negative x or positive x, so let us consider arbitrarily in positive x. So this is the body force, so bi in, so not bi, so b1. Okay, so b1 is the body force per unit volume into 1 by 6 od into area of ABC. Okay, that is od, so d is the point, okay, here. So od is the perpendicular distance from O to plane ABC. Fine. Okay, so no other force is acting. Now writing a force balance, so what do we learn? So force balance along, okay, let me take another color, so maybe this. So force balance along x1 direction. Okay, so that will give what, sigma 11 area OAC plus sigma 21 area OAB plus sigma 31 area what, OBC, minus this into ABC plus, or yeah, minus, so B1 1 by 6. So I am not sure about this constant 1 by 6, but this will be either 1 by 6 or 1 by 3, just check in internet, this will not matter actually for the derivation. Okay, so this is equal to mass times acceleration. So, okay, so external force equal to mass times acceleration. So this will be what, so mass will be volume, that is 1 by 6 OD area of ABC, right, into rho, that is mass time acceleration along 1 A1, right. Now how can we relate area of ABC and OAC, OBC and OAB, and why we have to relate that? Okay, because here we have to derive a relation for this sigma 11 sigma 1 to sigma 13 and this thing. So to derive that relation, we must have to know the relation between these areas, all these four areas. So I think it is this is pretty obvious that we know that area is a vector, right? Area is a vector having the magnitude of that area and the direction along the surface normal. So let me give you a concept, and this concept is already known by all of you. So if v is a vector, okay, so then it will have its component along x1 x2 and x3. So let me introduce the unit vectors given by e1 cap, e2 cap and e3 cap. So essentially you can think these as I cap, j cap, k cap. So I can tell you that can you tell me that uh, this is what? So this is the projection, right? So this is the projection of v, okay, towards x1, right? Similarly, if I have this area ABC, okay, so this will be given by what, the magnitude into the surface normal, right? Now if I have to project this area onto the x1 direction, so then I will have the component of area ABC um, in x1 direction, so that is equal to area ABC, so this area vector dot e1, right? So this will be this thing dot this, I can write it. Now what is n1 dot u1? So if I can write that n1, so n1 cap equal to, okay, so n1, so n is a vector, okay, I have write it as n, so n equal to n1 e1 plus n2 e2 plus n3 e3, okay, so n3 e3. Now so this will be what? So this will be what? N1, right? So this is area of ABC into N1. Now what do you mean by projecting an area, right? So mathematically, if I am having the unit normal of ABC towards this direction, then I am projecting this unit normal towards x1 direction. Then the projection will be in the direction of x1 direction. So which area is actually having the normal along the x1 direction or parallel to x1 direction, that is area of OAC. In other words, if you blow a torch from this side, if you blow a torch from this side, okay, to area of ABC, then it will project an area that will be on the plane, uh, on the plane given by the coordinate axis x2 and x3. So it will project an area of area equal to OAC, okay. So that means essentially this area is area of OAC, right? Is area of OAC. Similarly, if I do area of ABC into N2, so which surface is having the direction normal parallel to x2, that is OAB. So it will be area of OAB. Then area of ABC into N3 must be area of OBC. Now put these things, okay, now put these things into this equation. So just we don't have to remember, I can lasso it, okay. So I think this will be enough here, okay. Okay, so we have to keep in mind this section, okay. So now in place of area of OAC, I can write what? N1 into area of ABC plus, here OAB is N2 into area of ABC plus 31 is what? N3 into area of ABC, and a sigma 31 is there, minus T1n area of ABC minus B1 by 6 OD area of ABC equal to OD by 6 area of ABC rho A1, right? So now on this whole expression apply limit OD tends to 0, okay, on this whole expression, okay. So then what will we get? So doing OD tends to 0 means every dimension AB, AC and CV all are tending to 0, that is the tetrahedron is converging towards a point, okay. So then these terms will go, right, will be neglected, and so we'll be getting this term, that is sigma 31 n3 equal to T1, right? Now we will approach this by Einstein indices notation. Okay, so we can write this as sigma. Okay, so here which index is repeating or which number is repeating? So this one, this one, this one, so this is repeating, right? Okay, so this is repeating in various terms, but in each of the terms, so this is a term, this is a term, this is a term, so in each of the term, which of the index is repeating, right? So in this term, okay, this term, this one and this one is repeating, and in this term, okay, this 2 and this 2 is repeating, and in this term, okay, um, this 3 and this 3 is repeating. Okay, so I can write it as sigma of uh, ji in j, so j will run from 1 to 3, is equal to, okay, tin. So here this term will represent each of this term. Okay, and in, so here j is the repeated index, so for this j is repeated index and I is a free index. So in both of the sides, in both of the sides LHS and RHS, we have this free index I. So both are vectors. So only one free index and one repeating index. So if it is having only one free index, then it is vector. Okay, so the by Einstein indices notation, we are having this thing. Okay, so this is one of the most important uh, results for the continuum mechanics, very very important. Okay, and this is known as Cauchy's theorem. Okay, okay, so uh, for today's discussion I will stop here because the battery of my mic is going down. I apologize for that. But what I will share with you, that is, listen, I am not omitting or I am not avoiding any part. Okay, that is, I have started from the tensor notation, so that there will be various aspects of this derivation in which we will get the application of this indices notation. Okay, so that is why those tensor notations and the concept of the first order tensor, the vector, and how to apply those tensor notations or those indices notation in the equations, that also I have tried to convey to you. Okay, and I am also deriving each and every part of the derivation, because uh, I don't want you to hear the thing that you assume this, or you just believe me this happens. Okay, because I find that if I will tell you that you can that that is, I could have told you that just you believe me that this is the Cauchy's theorem, and this is taught in various fluid mechanics courses, and you just go and learn from there. Okay, either in a fluid mechanics or in a solid mechanics course. So in the middle of the derivation of anything, if you get any doubt or any part that remains unsolved, okay, then that will be then that will be an uncomfortable situation for you. Okay, and I believe that that is hindering the learning process. So I will make sure that any part of the derivation you don't have to go to any other lecture or any other class or any other book. Okay, you will get the whole thing in this discussion only. So that is why this is taking time. If I don't tell all of these things, then these things will not take time. Okay, and so um, okay, so until next time, take care of yourself, and also let me know if there's any suggestion on this series or on my teaching method, or if you have any doubt.